the laws of signs in integers work, but again, this is actually more general. So, I mean, what I'm about to write is certainly true for us with integers, but it also goes beyond that. And you can guess what it is. Look, in this circle over here, we already know what, we know the definition of NA when n is a positive integer. So let's make n a positive integer, but multiplied by negative a. And again, this was property 4 of a ring of our ordered integral domain. So again, this is well defined. We've already, over here in the circle, we've defined a positive integer. In this circle here, we've defined a positive multiple of an element of the set. In our case, that element is a number. So this n in front of the negative a, okay, that's defined by what's in the circle here. And then negative a, yeah, that's an element of the ordered integral domain. For us, the ordered integral domain that we're talking about is the integers. It's z. And so we have defined integral multiples of any number. And as I say, it goes beyond that. But for us, we've now told what it means to write NA when n is positive, negative, or 0, and an integer, of course. Let's define here recursive definition of integral. And as I've said a number of times, integral, as I'm using it here, is an adjective for integer. Integral exponents. So we start with n being a positive integer. So of course, again, no surprise, we'll define a to the power 1 to equal a itself. And so now we have the definition of a to the n, recursive definition of, so what we're defining here is a to the n. All right, so here we have the definition when n equals 1. And now we will provide the definition for n plus 1. And again, we will define that, not surprisingly, to be a to the n times a. And again, by closure under multiplication, this is defined, and if a to the n is defined, then a to the n times a is well defined. And so this gives us an inductive definition of a to the n, where n is a positive integer. So that's the whole definition. When a is a positive integer, we'll get to the other cases in a moment. So again, that's the definition. Now, as I said before, to prove that this definition really covers all integral exponents, or at least so far all positive integral exponents, then you would have to say, if it's defined when the exponent is n, then it's defined when the exponent is n plus 1. So we've defined a to an exponent n plus 1 in terms of a to the nth power. Now, and this is as far as we'll go in our class, but just to be complete with the definition. If a is not 0, and by 0, well, for us again, we're just dealing with numbers, so here I mean the number 0. More generally, if you have an arbitrary ring, when I write a is not equal to 0, I just mean a is different from the additive identity. But I'll go into that further next term. So here we define, again, no surprise here, a to the 0th, you know what it'll be defined as. It'll be defined as 1. You know, where that comes from is this is not part of the proof. I'm just, if you just, let me just show you this if you're interested. A to the 0th can be written as a to the power 1 minus 1. Under what circumstances, with what operation do we subtract exponents? Well, for instance, if you have a to the 5th over a squared, what's that? This is a times a times a times a times a over a times a. Two of the a's cancel, they divide into 1, and you're left with a to the 5 minus 2, or a to the power 3. So where does subtraction of exponents come from? It comes from division. So a to the 1 minus 1 can be written as a to the 1 over a to the 1, because just like over here, when you have the same base, a in each case, numerator and denominator, two powers, the result is that same base, a is the base, to the difference of the exponents, numerator minus denominator. And so any non-zero, you see why we need a is different from 0, right? Because a is in the denominator. Any non-zero number divided by that same non-zero number is 1 by the definition of division. What does it mean to say a to the first divided by a to the first equals 1? Means a to the first, multiply both sides by a to the first, and you get 1 times a to the first. And since 1 is a multiplicative identity, a to the first does equal a to the first. So let's observe, in fact, 0 to the 0th power is not defined. So a over here, a has to be different from 0. If a equals 0, here you have 0 to the 0th power, and you'd have a problem over here. Now, why is this not a proof that a to the 0th equals 1? Well, you know, it's not proof because how do you know that in all cases, yeah, with a bigger positive number here and a smaller positive number here in the denominator, you subtract exponents, but that doesn't say anything about if the exponents are not a bigger number over a smaller number over here. How do you know that in order to subtract, in order to divide like bases, whether the exponents are the same or the exponent in the denominator is bigger? How do you know? Over here we can do it by counting. As I said, this is a to the 5th is a times a times a times a times a, and then you divide out a times a, and you're left with a to the 3rd. But how do you know that this is a to the 2nd minus the 3rd? Well, you don't know, but we like consistency in mathematics. We don't want to have to learn separate rules for all sorts of different cases, and also it unifies mathematics. So here's why we define this to be a to the 2 minus 3. If you want the same laws of exponents to work when the denominator exponent is bigger than the numerator exponent, then we want to have the same rule, namely that over here, to divide like bases, you keep the same base a and subtract the exponents. So if you want consistency, here we have the same base a, in the numerator, a in the denominator, keep the same base a, and do the same as you would over here, namely define a to the 2nd over a to the 3rd to be a to the 2 minus 3, which equals a to the negative 1. But this is the reason for a to the negative 1 to be a fraction, if you write what this is, the numerator is a times a, the denominator is a times a times a, and now a divided by a is 1, a divided by a is 1, and so you're left with 1 in the numerator and a in the denominator. And so, if you want, and we do, if you want the laws of exponents to be consistent, no matter what the exponents are, whether the numerator is bigger, the exponent in the numerator is bigger than the exponent in the denominator, or the other way around, like over here, if you want the same rule to hold, then that obliges us to define a to the negative 1 to be 1 over a to the positive 1. So that was just sort of an aside, just bringing up something that you've, quote, known for a long time, but maybe not really, or didn't understand it, or you kind of just accepted it. So this is not part of what I'm doing. Let's get back to over here. If a is not 0, because you have the same sort of thing as we have up here. If a is not 0, we will define a to a negative power. Again, up here we defined, over here, we defined a to the nth when n was a positive integer. What about a to a negative power? Well, again, you can guess what we're going to do. This will be defined to be a to the negative 1 to a positive integer power, which we've defined up here in the box. I'm putting this in for the sake of completeness and to show the full induction, although for us, again, we've mentioned this before.
Dr. Friedland, is that parentheses a to the minus 1 to the power of n or multiplied by n?
Oh, that's an exponent. Yeah, sorry. Yeah. Okay. So, so if you have multiplicative inverses, remember a to the negative 1 is the multiplicative inverse of a in either order. A times a inverse has to equal 1. So that's the definition of a inverse. So we don't have that in integers, but just for completeness, and because you've probably seen this elsewhere or will see it, I'm just mentioning, I think the first day, or if not the first or second day, one of you mentioned the field. I think I know who did. So in a field, that's the main distinction. It's a commutative ring with unity with non-zero elements having inverses, like A inverse. So in a field, every non-zero element has an inverse. That's the definition of field. Okay, so think about that. That's kind of neat that we can give a rigorous definition based on mathematical induction of exponents and coefficients, and there are other places where you give inductive or recursive definitions. The next thing, so at the top here, I wrote that I want to cover recursive definitions, the greatest integer function, and then spend the rest of the period going over some of the homework that I've been asking you to do. So let's just give, this will look trivial, but it's actually a function that's very often used in number theory. It's called the greatest integer function. And because it's written with brackets, it's sometimes called the bracket function. And as I say, it's written in square brackets. Is the largest or greatest or biggest integer. And some books will write this, but I think we should define it in X. What does that mean? It means the biggest integer that is less than or equal to X. Or to put it another way, it is the unique, means just one, number, well, the specific integer, m, such that or for which m is less than or equal to x is less than m plus 1. So you see, m is less than or equal to x, but it's less than the next number, because if it weren't less than the next number, then the next number would be a bigger integer. We want the biggest integer that's less than or equal to x. So let's take some examples. So the greatest integer less than or equal to 7 is, of course, 7. The greatest integer less than or equal to 7.1 is still 7. The greatest integer less than or equal to 7.99, so that's less than 8. So the biggest whole number less than 7.99 is 7. How about bracket pi? What would that be? So remember that pi is 3.1415926535. In any case, it's 3 point something. So this is approximately 3. I'll just do it to 2 decimal places. And so we see that the greatest integer less than or equal to 3.14 is 3. Let's take a look at the bracket function for negative numbers, say this. What's the greatest integer? So look. So the number line, the way I've drawn it, is increasing to the right. So you want the biggest integer, the rightmost integer, that is less than or equal to -2. Well, clearly the greatest integer that is less than or equal to -2 is -2 itself. Let's take a look at, say, -2.5. Okay, looking at that number line there, what's the greatest integer less than or equal to -2.5? So this time it's going to be -3. Over here is the rightmost, the greatest, it's increasing, the rightmost or the greatest integer less than or equal to, in this case, strictly less than -2.5. So the bracket function for an integer is just that same integer. Okay, let us now, unless anyone wants to say anything or has any questions. If so, unmute yourself and bring them up. If not, we will proceed to spend the remaining half hour going over homework, which I have here. So, okay, then. Again, feel free to stop me if there's anything you're not following, or make a note. And assuming we stay on for the full period, the way we managed to on Tuesday, then I'll come back to you at the end. And if anyone still wants to talk, we can do that. And eventually, hopefully in the coming week, I'll learn how to use the waiting room to talk to you individually if you want, and send you documents and send you all the notes for the term. But okay, so then let's continue with the sheet, which I hope to be able to get to you, but instead I've been writing it, that I call forms of integers. Okay, all right, so we did the first two of them where we proved that the square of a number is even if and only if the number is even, number meaning integer, and the square of an odd, if the square of an odd integer is odd, and conversely, if the square is odd, then the number itself is odd. So let's go on to number 3. Okay, let's see. The product of two consecutive integers is divisible by 2. So consecutive means one right after the other, like Tuesday, Wednesday, and Thursday are 3 consecutive days of the week. Consecutive numbers are like 8, 9, 10, 11, one right after another. And I've mentioned the idea of a discrete set, spelled this way, as opposed to spelled this way, which means have some discretion, be careful of what you say. Discrete means separate and distinct. We used to teach a whole class called discrete mathematics, and it dealt with things that are not calculus like continuous. So we did graph theory, a little bit of number theory, simple probability, electrical circuits, things that were discrete as opposed to continuous. Well, speaking of divisible by 2, let A, B, and Z, then from the division algorithm, A equals 2Q plus R, where R is less than or equal to the absolute value of the divisor, which is 2. If the first number over here, 2 consecutive integers, if the first integer is of the form 2Q, the next consecutive integer is 2Q plus 1, and of course, their product is 2Q times 2Q plus 1 equals 2 times. Okay, so again, by closure, if q is an integer over here, 2q is an integer, 2q plus 1 is an integer by closure. By the associative property, we can put those two together and leave the 2 alone, right? The associative property 7 of any ring, you can associate multiplication. And so by closure, this is some integer.
Dr. Friedland, can you clarify what is that you wrote? Their product is, and then
Yeah, the product is, so the product is 2q, that's the first one, times 2q plus 1. That would be the next one, right? What's the definition of two consecutive integers? If the first one is n, by definition, the second one is n plus 1, right? And the one after that would be n plus 1, which would be n plus 2. So those are consecutive integers. n plus 1, n plus 2, if you have a fourth one, n plus 3, and so on. So over here, what I said is, in this box over here, by the division algorithm, whatever number you have, a, if you divide by 2, it equals 2q, right? 2, the divisor, times a quotient, plus a remainder, which to save writing it twice, I wrote it this way, plus 0, or 2a equals 2q plus 1. So let's look at the two possibilities. If over here, if the first number is 2q, then the next one is 2q plus 1. And so the product is 2q times 2q plus 1. And what I'm saying is that by the associative property, you can group those, the associative property for multiplication, and since q is a number, that 2q is a number by closure of the numbers under multiplication, and then 2q plus 1, so 2q is a number, and if you add another number, 1, by closure under addition, this is a number. It's not something else, it's a number by closure. And again, now a number times q is also a number. Supposedly over here, call it n, call it k, call it whatever you want. Then the product which was over here, that's the product. The product 2q times 2q plus 1, the product of those two consecutive integers, can be written as 2 times this number. And by definition, 2 times an integer is even. That's if the first number is 2q. So there's another possibility over here in this box. The first number could be not 2q plus 0, but 2q plus 1. If the first number is 2q plus 1, the next, and it's redundant to say the next consecutive integer. Next means consecutive, consecutive means next. So I'll just say the next integer is 2q plus 1 plus 1. I'll just write 2q plus 2. Which equals 2 times q plus 1. And by closure, this can be written as 2 times k, which is even. So the product of these two numbers, the first number is 2q plus 1, the second number is 2q plus 2. The product that we're looking at, this is what we had to show, that the product of two consecutive numbers is even. So the product is 2q plus 1 times 2q plus 2, which we just found over here was 2k. And if you want to rewrite that by using the associative law to put these two together, and then the commutative law to put the two in front, if you want to have it exactly that way, this equals 2. If you want to put the k in next, it doesn't matter. The order doesn't matter because of commutativity. So you're just putting a k first. You don't need that. So it's 2k times 2q plus 1, which can be written, if you want to be very formal and write every detail down, if you call this, say, m, this equals 2 times m, which again is even. So we had in both cases that whichever you start with, the product is even. Okay, I've written that in excruciating detail. Now, let's go to number 4. And you know what? Although I'm going over these, you should rewrite them unless you're confident that you did them, very well. But if not, or if you had trouble with them, with this, write it out yourself so you know how to write a proof. So there's some controversy about how you write a proof. The sum of an integer and its square. The sum, this is what we want to prove. The sum of an integer n and its square we want to show that that is even. All right, so you want to take a look at the sum. This is the sum of an integer, that's n, and its square, n squared, is even. Well, let's look at this in two ways. One way is to, by the distributive law, except in this form you call it factoring, if you take out an n, you have 1 plus n, or, the order doesn't matter, n times, if you want to see it as n plus 1. And what's that? That is precisely the product up here from number 3 of two consecutive integers, right? N and n plus 1, which is the product of two consecutive integers. By the way, I arranged these so that in many cases you can use a previous result to simplify the one you're working on. And from the last example, is even, which completes the proof. But okay, suppose you didn't notice that. So another way to look at it would be to say, if n is even, well then from question 1a, n squared is even, and the sum of two even numbers
Hindi. Mo ayaw klase siya sa tinong klase saro.
What's that? No, well, okay. Insofar as possible on a test, just as I try to make my classes as self-contained as possible without referring unnecessarily to other classes. I mean, I refer to other classes to show you connections in mathematics, but I try to make my classes themselves academically independent of each other. And the same thing for questions on a test. No, on a test, you not only can, but should cite theorems, things that we've actually proven as theorems, but I would try not to. Well, the answer to the question is no. I mean, you can't say, "Oh, we once proved." If it's a theorem, you have to cite the theorem. Yeah, you can't say by a previous theorem or by something we once proved. If you're using something on a test, you have to explicitly say what it is. And if in fact it's a theorem, that you don't have to reprove. But a passing example that we've done. As I say, I would try to avoid a question that would refer to something like that and try to make it self-contained, but you really have to, if you're using antecedent, that means prior, earlier information, you're welcome to if it's a theorem, but you have to cite and state the theorem. So, before a test, I will try to go into some more detail. Okay, so over here we have if n is even, but if n is odd, and what I'm doing now, maybe the idea may be helpful in question, is it 16 maybe? If n is odd, so we're looking at the sum of an integer and its square. So from question, what is it, 1A, 2A. So if n is odd in n plus n squared, from 2A, n squared is odd, right? We showed in question 2A that if n is odd, n squared is odd. So n plus n squared, I'm talking about over here, if n is odd, then this is the sum of two odd numbers. Right, I'm saying if n is odd, then n is odd, and we proved that if n is odd, n squared is odd. So we have the sum of two odd numbers, which is, can you finish that sentence in 50 words or less? Like one word? Like even? The sum of two odd numbers is even. Yeah, is even, as was to be shown. Oh, right, yeah, product, yeah. Yeah, I mean, you should certainly easily be able to prove that the product of two odd numbers is odd. Write this down if you don't see it or you can't immediately. Prove that the product of two odd numbers is odd, and the sum of two odd numbers is even. The product of two odd numbers is odd, and the sum of two odd numbers is even. So how do you write two odd numbers? Well, let one be two. Now, I'm not saying the same odd numbers, so they have to be different. So if you let one odd number be 2k plus 1, right, that's an odd number. The other number would be 2, say, j plus 1, okay? And show that if you multiply them, the result is odd. In other words, it's the form 2 times some number m plus 1, and the sum is even of the form just 2 times m. Let's look at question 5. Where we want to show that all integers they are of the form 3k plus 1 or 3k minus 1. Okay, so again, number meaning integer. And you have to give a reason for everything. So the reason for what I'm going to write is the division algorithm. So again, that's a theorem that you not only may use, but should use. You're not going to start from scratch with that. We have a equals, if you divide by 3, you get r, where the remainder r equals 0, 1, or 2. Okay, so if r is 0, a equals 3k, and that's the first possibility over here. If r equals 1, then for the second possibility over there, circle around that, we have a equals 3k, or q, or whatever you're calling it. I guess I called it k here, plus 1. Right here, r has to be one of those. You don't have to be this careful, but I'm going to be very careful here. You'll see why in a moment. Instead of calling it K, I'll call it Q. Now, over here, over here, this box, I want to get it into the form -1. So if I want a -1, I'll put a -1 there. But so I want to get this 2 to be, let me show it this way. So I want to get over here, a -1 there, so that it is of this form. But I had a 2 here, and now I'm changing that to -1, so I have to compensate for that. I mean, I can't change the 2. The 2 has to be there. So I'm doing what I always do and what you always do in mathematics. I'm changing the form, but not the value. So what should I do here? In order to get from 2 to -1, I subtracted 3, so I have to add 3, right? So do you agree that what I have over here actually is the same as what I have over here? In value, not in form. 3q plus 2 equals 3q plus 3 minus 1. And let me rewrite it in that order. 3q plus 3. So now I've separated it out to -1, so it looks like that. So I'm trying to work it into this form. So I want to have a -1 at the end. Okay, so now I have -1. And then this equals, but now I have to show, again, I have to show that it's 3 times some number, k, minus 1. So I want to get it into the form 3k minus 1. So, right, so I wanted it as 3 times something. So by the distributive property, call it factoring if you like, take out the 3 in 2 places and be left with q plus 1 minus 1. And so we're getting there. I'm being very formal and very careful now. So again, by closure, this q plus 1 is an integer. And now you'll see why I chose q instead of k. In which case, this is written as 3k minus 1, which is what we wanted there. I did it that way. Basically, I could have used k instead of changing it to q, but then over here, I would have gotten k plus 1, but I don't like saying, okay, so let k plus 1 equal k, so that it looks just like that. So I chose another letter. Okay, let's,
Professor, are you there? He is in a tablet, bro.
Professor, we can see you writing, but we cannot hear you.